Hello everyone, once again welcome to this channel. Today's topic is Born Lande equation. This time I am not writing on the board, instead I have prepared this PowerPoint presentation for better clarity of the picture. Hope you will enjoy this lecture and it will be helpful for you. Now let's begin. So before going into Born Lande equation, let me tell you what is lattice energy. You all know this probably. Still I am explaining it to you. Lattice energy is the amount of energy released during the formation of 1 mole of solid lattice when it is thought that the two component ions are at infinite distance and they are being brought to their bonding distance. So the information of this lattice energy for a particular compound is very important in order to know their stability. Now there are several ways in which we can calculate lattice energy, and Born Lande equation is one of the ways. And in 1918, first these two scientists, Max Born and Alfred Lande, proposed this equation, and they assume that if we can calculate the potential energy of a particular solid lattice, then we can get the information about its lattice energy. So before going into the derivation portion, let's have a look of the assumption they made of this in order to derive this equation. They thought that the ionic crystal must be constructed by a regular orientation of the oppositely charged ions, and obviously according to them these ions must be hard sphere, incompressible hard sphere. Secondly, they assume that within a crystal the ions are held together by electrostatic forces only. Okay? And thirdly, they assume that within the crystal, in addition to the Coulombic forces, that means attractive forces between the oppositely charged ions, there is also a certain amount of short range repulsive forces. Okay? Why these repulsive forces? Because when two oppositely charged ions approach each other, their nucleus will attract, but their electron clouds will repel each other. Okay? Due to the interpenetration of their electronic clouds, there will be a certain amount of short range repulsive potential or repulsive force also present in the crystal lattice. And fourthly, lastly, they assume that at the equilibrium position, these attractive and the repulsive forces should get mutually balanced. So let's have a look on the derivation of this Born Lande equation. So obviously what we will try to first note down, we will just first try to calculate the potential energy of a particular crystal lattice. Now this we all know that if we have an ion pair, say Mx, where M is the cation with charge number Z plus and X is the anion with charge number Z minus, then when they are brought from infinity to a particular distance, say R, then the electrostatic energy of attraction, which we call the Coulombic potential, must be directly proportional to their charges of the ion, both cation and anion, product of their charges, and it will be inversely proportional to the distance R. Now see, it is given by the equation, and here you can see that this Coulombic potential has a negative sign. Why negative sign? Basically the potential energy is of a system of point charges is actually the amount of external work that has to be done in order to bring the point charges at their respective position from infinity. Now we know that unlike charges attract each other, so obviously when they are approaching each other, we don't need any external work to be done, and when they are approaching from infinity, obviously their potential energy will goes on decreasing, and in order to denote this negative sign is put in front of the equation. Now see, in a total crystal, in a crystal lattice, there is not a single ion pair. Obviously it will consist of several ion pairs, isn't it? Now we can thought that the summation of their geometrical interactions within an entire lattice is given by a constant, and this constant is the characteristic property of that particular lattice. Okay, suppose say I have a compound which assume NaCl type of structure, then that compound in the NaCl type of structure have a particular Madelung constant which is denoted by A. So obviously the previous equation of Coulombic potential will simply be multiplied by this factor of the constant, that is A, in order to get the total Coulombic potential in a particular crystal lattice. Now we already know that Born suggested that there must be a repulsive potential too, and it is given by this equation capital B by R to the power n, where B is called the repulsive coefficient in a particular lattice, and it is also constant, and n is called the Born exponent factor. We will see in our later slide that from where this n is coming, how it is related to a particular element, okay, or particular ion. Now see, this is my EC equals to my Coulombic potential and ER equals to my repulsive potential. Then obviously the total potential energy for 1 mole of crystal lattice, which contains a Avogadro number of ion pairs, is thought to be the summation of this Coulombic potential and repulsive potential. And you can see from the slide, I have just written the summation of the two potential, and it denotes the potential energy of my 1 mole of crystal lattice. Now let's have a look at this graph. I have said you earlier that when two unlike charges approach each other, their potential energy goes on decreasing. Attractive potential energy and their repulsive potential energy goes on increasing. So obviously we can draw a resultant graph. It is shown in the graph in between, and the position you can see that at a particular point, okay, at a particular distance, this potential energy is minimum. Now this particular distance where the potential energy is minimum, we can say that at this particular point it is the equilibrium position. That means the attractive potential and the repulsive potential, or the attractive and the repulsive forces, get mutually balanced. Now this is the point where the bonding occurs, and we can say these distances are not as my bonding distance for that particular crystal lattice. Now the potential energy corresponding to this bonding distance is my desired lattice energy. So if I can apply the condition of minima, that means if I can do the derivative of my potential energy equation with respect to my internuclear distance and apply the condition of minima, that is du dr equal to 0, we will get our lattice energy. So just do this mathematical transformation and you will get this equation. I am not going into the details of this derivation. You all know this from your class 12 standard. Okay. So after rearranging, we can have a value of the repulsive coefficient B in terms of this Madelung constant, charge number E and N. Now just do one thing, put this value of B in the above equation of the potential energy. Then what we will get, and replace R by R naught, because I am doing the derivative at the condition of minima, where we are assuming that the internuclear distance is my bonding distance. So after doing this, we are getting the equation for my lattice energy. So this is basically the Born Lande equation. Now we will just do a little bit rearrangement and we will put the value of the numerical constant in the above equation to get my desired format of Born Lande equation. So this is inside the box what you are seeing. This is my Born Lande equation, which you have to remember. In your exam, this derivation will come also. It may come also, and also you will be asked some direct question from this Born Lande equation. So for that purpose, you need to understand this derivation portion very well to attend this format, and also you have to remember this Born Lande equation in this form. So one thing you must remember when you will be directly given question on this Born Lande equation, the value of internuclear distance should be put in picometer unit in this equation. Otherwise, your result will be redundant. In your question, the value of R0 may be given in centimeter, may be given in meter, may be given in angstrom unit. What you need to do? You need to first convert it into the picometer unit, then put it in my Born Lande equation, and you will get the answer in kilojoule per mole. So students, this is all about Born Lande equation. Now, let's have a look at this chart. I have already said you that I will show you this chart of Born exponent and Madelung constant. I am telling you one thing, for upcoming board exam, no need to worry about these charts, because in your board exam you will be supplied with the Born exponent and Madelung constant values. It's okay. But for your higher, further competitive exams like NET, GATE, or jam, etc., you will not be supplied. Then you have to remember these values. Just see, it's very simple. Here in the Born exponent chart, you can see in the left hand side in the blue, there are given the electronic configuration of some noble gases, some ion, helium, neon, argon, krypton, xenon. And in between in the red, they are given their corresponding Born exponent value, that is 5, 7, 9, 10, 12. And at the right hand side, they are giving some example. Okay, that means which cation and which anion will correspond to that particular electronic configuration. Say for example, I have given one compound, lithium chloride. Okay, try to understand lithium chloride, NaCl. Now see, the lithium plus ion in the chart, you can see it assume helium type of configuration. So obviously it will have Born exponent value N equal to 5, and chloride, see from the chart, it is assuming argon type configuration. So obviously here its Born exponent value will be 9. So for the compound lithium chloride, what will be the Born exponent value? 5 plus 9 divided by 2. Simply the average. Okay, got it? How to calculate the Born exponent? Now see, this chart shows the Madelung constant value for various lattice structure. I have mentioned earlier also that it is a characteristic property of the particular lattice. If my compound assume NaCl structure, its Madelung constant is 1.7475. This is the most common question which is asked in various examination, and also to some extent cesium chloride. Other two also try to remember, but these two, the first two is very important. Okay. Now see, there are some cases where the lattice type is unknown. Obviously, if the lattice type is unknown, we don't have any idea about the Madelung constant. Okay, because it is a characteristic property of the lattice structure. Then what to do? We cannot use Born Lande equation to calculate my lattice energy. At that time, to overcome this difficulty, Kapustinskii proposed the following equation. Just see, I am not going into the derivation portion of this equation because it is not in our syllabus. Only I am writing the final format of the Kapustinskii equation. You just remember this equation in this format. And in this equation also remember R0 value should be put in picometer unit. Okay. Here the only difference is one factor, that is mu. Here A is not there, N is not there. Instead it is replaced by mu. What is mu? Mu is nothing but the total number of ions per formula representation. For example, I have NaCl ion, ionic compound. So 1 sodium, 1 chloride, mu equal to 2. I have calcium fluoride, 1 calcium, 2 fluoride, mu equal to 3. Don't go with their charge numbers. Okay, only the number of ions. So this is all about Kapustinskii equation. Now let's move to the last section of my lecture, that is the application of this Born Lande equation. Obviously you know that you will be asked this type of question where directly you will be given to calculate the lattice energy of a particular compound and some data will be given to you. This is a bit harder type. You will be asked more easier type in your board exam. See what it is telling over here, that calculate the lattice energy of rubidium bromide adopting the rock salt structure, and given is the radii of the cation and the anion. So first what we need to do, we need to write the Born Lande equation as we have seen in our earlier slide. Now here in the Born Lande equation we need to put the value of A, Z plus Z minus, R0 and N, and then we will get our result. Now see, here in my question the radii is already given in picometer unit, so no need to convert the units. Simply what we have to do, we have to add the radii of the cation and the anion to get my internuclear distance. I have shown in the slide. And see here, both rubidium and bromide have one charge. Charge number is 1. Don't go with the sign +1 -1. Only go with their charge number, that is 1. And since it is a rock salt structure, that means NaCl type structure, we have seen in our earlier slide that the Madelung constant should be 1.7475. And see, here the Born exponent will be what? That rubidium plus and bromide plus. You can go to the previous slide and see both adopt krypton configuration. That means both will have 10 bond exponent. So the average of 210 is again 10. So just put these values in our Born Lande equation and you will get the desired result. So this is one type of question which is the most common type. Now see, another type may be asked to you that they will directly not give you any data. Only they will want to know the comparison between two compounds, say lithium fluoride and cesium iodide. They are telling that among them which one is thermally more stable. So obviously the compound which will have more lattice energy will be thermally more stable. Now see, here no data is as such given, so no, we cannot calculate lattice energy, we can only compare the lattice energy. We know from Born Lande equation that is lattice energy is inversely proportional to the internuclear distance. And internuclear distance is nothing but the summation of the radii of the cation and the anion. Now in our question, both lithium plus and F minus are smaller ions compared to cesium plus and I minus. So obviously the internuclear distance in lithium fluoride crystal will be less compared to that in cesium iodide crystal. And inverse will happen to their lattice energy. That means lithium fluoride will have more lattice energy than cesium iodide, and hence we can say that larger the ions, the smaller will be the lattice energy. And obviously our lithium fluoride having more lattice energy will be thermally more stable. Now similar type of question in another format may ask to you that among lithium fluoride and magnesium oxide, whose lattice energy is more. Now see here, like before, lithium and magnesium, the two cations do not belong to the same group. Neither the anions, that is fluoride and oxide, belong to the same group. So directly we cannot compare their radii or the internuclear distance. Again we know from Born Lande equation that lattice energy is directly proportional to the charge number of the component ions. Now see, in lithium fluoride it is a univalent crystal. Both lithium and fluorine have +1 and -1 charge. But in magnesium oxide it is a bivalent crystal. That means magnesium also has +2 charge number, oxide also has -2 charge number. We know that we don't need to go with their sign, only the magnitude. Then obviously we can see, if we put this data, then the lattice energy of magnesium oxide will be nearly around 2 × 2, 4 times than that of lithium fluoride. So obviously it will be more thermally stable. Now another question, a bit different type, may be asked to you in this way. Just read out the question first. Why KCl adopts the NaCl structure though the radius ratio support the cesium fluoride structure, and the data, that means the radii of the ion in different structure is given. Now see, we know that from radius ratio we can predict the geometry, but here they are telling that KCl do not follow the radius ratio rule. So what to do? We need to calculate the lattice energy of this particular compound in both the structure. So for that we need to apply our Born Lande equation, and it is known to us that in Born Lande equation the Born exponent, that means N, it depends on the component ions, that means K plus and Cl minus. So obviously N will be same for KCl compound in both the structure. No need to bother about N. Only what will vary? Madelung constant will vary since the crystal structure is changing, and obviously the internuclear distance will vary. Also the charge number will remain the same. So we need to calculate only the internuclear distance, and we need to put the value of the Madelung constant for the respective lattice structure. So just let me calculate the internuclear distance for KCl in both the correlation, that means in both the structure NaCl type and cesium fluoride type. It is shown in the slide. Now just put this value in the Madelung constant and do the ratio of their lattice energy, and it is seen that the lattice energy of KCl in NaCl type structure is relatively larger, almost 3% larger than that in cesium fluoride structure. So obviously we can tell that is KCl adopts NaCl structure because here its lattice energy is more and it is more stable. So this is all about this chapter. Hope you have enjoyed the video and understand the topic very well. So please follow this channel regularly for further updates. Thank you for watching.